Speaking of strange and fascinating phenomena, have you heard of the Casimir effect, Albert?
Yes, the Casimir effect is an interesting manifestation of quantum mechanics. It's a force that arises between two closely spaced, uncharged metal plates in a vacuum.
How does that happen?
Well, according to quantum field theory, the vacuum is not empty but rather filled with virtual particles that constantly fluctuate in and out of existence. When two metal plates are placed very close together, the fluctuating electromagnetic field between them is restricted in certain wavelengths, creating a difference in the energy density of the vacuum inside and outside the plates.
So, what does that have to do with the Casimir effect?
The difference in energy density results in a force that pushes the plates towards each other. This force is known as the Casimir effect.
That's fascinating. So, the vacuum is not really empty but filled with virtual particles that can have a physical effect on matter.
Yes, that's correct. This is another example of how the quantum world can affect the macroscopic world in ways that were not predicted by classical physics.
It's incredible how the rules of the quantum world can produce such strange and fascinating effects in our everyday world.
Indeed, the Casimir effect is not only of fundamental interest but also has practical applications, such as in the design of microelectromechanical systems and in the study of quantum field theory.
Speaking of quantum field theory, can you tell me more about it, Albert?
Sure, quantum field theory is a framework that combines the principles of quantum mechanics with the concept of fields. In this theory, particles are not seen as isolated entities, but as excitations or waves in a field.
Interesting. So, does this mean that particles interact with fields?
Yes, that's correct. In quantum field theory, particles interact by exchanging virtual particles that carry the fundamental forces, such as the electromagnetic force, the strong nuclear force, and the weak nuclear force.
And what about gravity?
Well, the theory of general relativity describes gravity as a curvature of space-time rather than a force carried by particles. So the challenge in quantum field theory is to find a way to describe the interaction between quantum fields and gravity.
That's a fascinating challenge indeed. It's amazing how these fundamental forces are all related in some way.
Yes, it is. And quantum field theory has been incredibly successful in describing the behavior of subatomic particles and their interactions with fields, as well as predicting the existence of new particles.
It's incredible to think about how far our understanding of the universe has come in just a few decades, thanks to the development of quantum mechanics and quantum field theory.
Indeed it is. And the more we learn, the more we realize how much we still have to discover. But that's what makes science so exciting.
You mentioned that quantum field theory has been successful in predicting the existence of new particles. Can you tell me more about the Standard Model of particle physics?
Yes, the Standard Model is a theoretical framework that describes the behavior of subatomic particles and their interactions through the fundamental forces. It's based on the principles of quantum field theory, and it's been incredibly successful in predicting the existence of new particles.
Can you give me an example of a particle predicted by the Standard Model?
Sure, the Higgs boson is one of the most famous particles predicted by the Standard Model. It was discovered in 2012 by the Large Hadron Collider at CERN.
And what does the Higgs boson do?
Well, the Higgs boson gives particles mass. In the Standard Model, particles are either massless or have mass because they interact with the Higgs field, which permeates the universe.
That's fascinating. So, the Higgs boson is responsible for giving mass to all the particles in the universe?
Yes, that's right. And the Standard Model also describes the behavior of other particles, such as quarks, leptons, and gauge bosons, which carry the fundamental forces.
It's amazing how much we've been able to discover about the universe through the study of particles and their interactions.
Yes, and the Standard Model has been incredibly successful in describing the behavior of subatomic particles. However, there are still some limitations to the theory, such as the fact that it doesn't include gravity.
So what's the next step in our understanding of the universe?
Well, that's the big question. We need to find a way to reconcile the principles of quantum mechanics and general relativity, which describe the behavior of particles on a small scale and the behavior of gravity on a large scale, respectively. This is the challenge of quantum gravity, and it's one of the most exciting areas of research in theoretical physics today. So, Tesla, have you heard of quantum computing?
Yes, I have. It's a relatively new field of computing that relies on the principles of quantum mechanics.
That's correct. In classical computing, the basic unit of information is a bit, which can have a value of either 0 or 1. In quantum computing, the basic unit of information is a quantum bit, or qubit.
which can be in a superposition of both 0 and 1 states.
That's fascinating. So how is it useful?
Well, one of the most promising applications is in the field of cryptography. Quantum computers can potentially break traditional encryption methods, but they can also be used to create new unbreakable forms of encryption.
That's very interesting. What other applications are there?
Quantum computers can also be used for simulations of complex systems, such as chemical reactions and materials science. They can also potentially solve optimization problems much faster than classical computers.
That sounds very promising, but I've also heard that quantum computers are very difficult to build and operate.
Yes, that's true. The technology is still in its infancy, and there are many challenges to overcome, such as maintaining the delicate quantum states of the qubits and minimizing errors.
It sounds like a very exciting and challenging field to work in.
Indeed it is. The potential benefits of quantum computing are enormous, and it is likely to revolutionize many areas of science and technology in the coming years. Speaking of quantum computing and cryptography, have you heard about quantum cryptography?
No, I haven't. What is it?
It's a way of using the principles of quantum mechanics to create secure communication channels.
That sounds interesting. How does it work?
Well, traditional cryptographic methods rely on mathematical algorithms to scramble messages so that they can only be read by someone who has the key to unscramble them. However, if an eavesdropper intercepts the key, they can also read the message.
I see. So how does quantum cryptography solve this problem?
With quantum cryptography, a sender can transmit a message in the form of a stream of photons. Because of the properties of quantum mechanics, any attempt to intercept the photons and measure their properties would disturb them, which would alert the sender and the receiver to the presence of an eavesdropper.
I see. So the receiver can detect if someone is trying to intercept the message?
Yes, that's right. If the sender and the receiver detect any interference, they can immediately stop transmitting the message and start again with a new set of keys.
That sounds like a very secure method of communication.
It is. In fact, it's believed to be theoretically unbreakable, because any attempt to intercept the message would change it in a way that would be detectable by the sender and the receiver.
That's amazing. I can see how this would be very useful for transmitting sensitive information.
Yes, it has many potential applications, including in military and government communications, as well as in the financial and healthcare sectors.
It sounds like another example of how quantum mechanics is revolutionizing the way we think about and use information.
I've heard about this so-called quantum teleportation. What is it exactly?
Quantum teleportation is the process of transferring the quantum state of one particle to another without physically moving the particle itself. It's based on the principle of entanglement we discussed earlier.
Interesting. How is it useful in practice?
Well, one potential application is in quantum communication. By teleporting the quantum state of a particle, we can transmit information securely over long distances without the risk of eavesdropping. This is because any attempt to measure the particle's state would collapse the state, and the sender and receiver would know that the communication was compromised.
So it's like a secure way of transmitting information. But how does the actual teleportation process work?
It involves creating an entangled pair of particles, one of which is given to the sender and the other to the receiver. The sender then measures the quantum state of a third unrelated particle and sends the result to the receiver over a classical channel. The receiver then uses this information to manipulate their entangled particle, which takes on the state of the original particle. It's a complex process, but it's been demonstrated experimentally.
Fascinating. It's amazing how quantum mechanics has opened up so many new possibilities for technology.
Yes, the concept of superposition is another fascinating aspect of quantum mechanics. It allows particles to exist in multiple states simultaneously until they are observed and the state collapses into a single outcome.
But how can a particle be in multiple states at once? It seems counterintuitive.
Well, it's because of the way particles are described by wave functions in quantum mechanics. These wave functions can be combined in a process called superposition, which creates a new wave function that represents a combination of the original states. When a measurement is made, the wave function collapses into a single state that corresponds to the measurement result.
I see. And this has practical applications as well?
Absolutely. One potential use is in quantum computing, where the ability to manipulate multiple states simultaneously allows for much faster and more efficient calculations than classical computers. Superposition is also important in quantum cryptography. where it allows for the creation of more secure keys for encryption.
It's incredible how something so abstract can have such concrete and important applications. The more I learn about quantum mechanics, the more I realize how much we still have to discover.
That's right, Einstein. One of the challenges in working with quantum systems is decoherence, which is the loss of quantum behavior over time. This occurs when a quantum system interacts with its environment, causing the quantum states to become entangled with the environment and leading to a breakdown of superposition.
So, does this mean that we can never fully control quantum systems?
Not necessarily. There are ways to mitigate the effects of decoherence, such as through the use of quantum error correction codes or through the isolation of the system from its environment. However, it remains a significant challenge in developing practical applications for quantum mechanics.
I see. And what are some other ways that decoherence affects quantum behavior?
Well, another effect of decoherence is the loss of entanglement between particles. Entanglement is a key feature of quantum mechanics, where the state of one particle is intrinsically linked to the state of another particle, even when separated by great distances. Decoherence can cause this entanglement to break down, leading to a loss of the quantum correlations between the particles.
Fascinating. It seems that as we learn more about the power of quantum mechanics, we also encounter more challenges in harnessing that power. Tesla, what do you make of quantum states and information?
Quantum states and information are fascinating. The quantum world is so different from our everyday world that it is hard to grasp.
Indeed, Tesla. Quantum states are strange and can be in a superposition of states. This means that they can be in multiple states at the same time.
Yes, that is correct. And in quantum mechanics, we measure these states to obtain information about the system.
That's right. However, measuring a quantum state can cause it to collapse into one state, destroying the superposition.
And that is where the concept of quantum entanglement comes into play. Entangled particles share a single quantum state, and measuring one particle instantly affects the state of the other particle, regardless of the distance between them.
It is an interesting concept, but I never fully accepted it.
Yes, you famously called it spooky action at a distance. But there have been experiments that have shown entanglement to be a real phenomenon.
That is true, Tesla. And the study of quantum states and information has led to new technologies such as quantum computing and quantum cryptography.
Absolutely. The potential applications of quantum mechanics are vast and exciting.
Speaking of quantum states and information, have you heard of the no-cloning theorem, Tesla?
Yes, I have. It's a fundamental result in quantum mechanics that states it is impossible to create an identical copy of an unknown quantum state.
That's right. And the theorem has important implications for quantum computing and cryptography. Without the ability to copy quantum states, we can ensure that messages sent using quantum encryption are secure.
That's interesting. Can you explain why it's impossible to copy quantum states?
Sure. The no-cloning theorem is based on the fact that measurement in quantum mechanics changes the state of the system being measured. If you try to copy a quantum state, you have to measure it, which changes it, and so the copy won't be identical to the original.
Ah, I see. So does that mean it's impossible to create a quantum computer that can copy quantum states?
Yes, that's correct. However, it is possible to perform operations on quantum states that can create new, useful states that are not simply copies of the original. This is the basis for quantum computing, which allows for much faster calculations than classical computers.
That's amazing. It's incredible how quantum mechanics has opened up a whole new world of possibilities for computing and cryptography.
Indeed, the potential applications are vast, and we have only scratched the surface of what can be done with this technology. So we've talked about the basics of quantum computing, but how efficient are these algorithms compared to classical computing?
That's a great question. Quantum algorithms are designed to exploit quantum phenomena to perform calculations faster than classical algorithms. For example, Shor's algorithm can factor large numbers exponentially faster than classical algorithms.
Interesting. And what about Grover's algorithm?
Grover's algorithm can search an unsorted database of n items in OSCART n time, while classical algorithms require ON time. This means that quantum computers can search very large databases much faster than classical computers.
That's incredible. But are there any limitations to quantum algorithms?
Yes, there are some limitations. For example, quantum computers can only solve certain types of problems efficiently. They are not a universal replacement for classical computers.
That makes sense. And how do we know if a problem can be solved efficiently by a quantum computer?
We use a concept called quantum complexity theory, which is similar to classical complexity theory. We can analyze the quantum circuit and determine its complexity and efficiency.
I see. So in summary, quantum algorithms can be much faster than classical algorithms for certain types of problems, but they are not a universal replacement for classical computers, and their efficiency depends on the complexity of the problem and the design of the quantum circuit.
Exactly. And as quantum computers become more advanced, we may discover new algorithms that can solve even more complex problems efficiently.
So we know that quantum computing holds great promise, but what about the issue of errors?
Ah, yes, this is where quantum error correction comes into play. The idea is to encode information into a larger quantum system so that it can be protected from errors.
But isn't that difficult to do since quantum systems are so fragile and easily influenced by external factors?
Yes, it is a challenge. But there are ways to minimize errors through techniques such as error detection and correction codes.
Can you explain more about how these codes work?
Sure, let's say we have a qubit, which is a quantum bit of information. If we encode this qubit into a larger quantum system, we can introduce redundancy so that if any one of the qubits gets corrupted or lost, we can still recover the original information.
That sounds complicated. How do we know if there are errors in the first place?
We can use quantum error correction codes to detect and correct errors. For example, we can use the syndrome measurement technique to determine the error and apply the appropriate correction. It's like a quantum error checking mechanism.
That's interesting. So quantum error correction can help reduce the errors that come with quantum computing?
Yes, and it's essential for building reliable and robust quantum computers that can perform complex computations without introducing too many errors.
It sounds like a crucial component of quantum computing. I'm glad to see progress in this area.
Absolutely. And as we continue to improve quantum error correction, we'll be able to unlock even more potential for quantum computing in the future.
So far, we have discussed quantum mechanics at the microscopic level. But can it be applied to macroscopic objects as well?
That's an interesting question, Einstein. The answer is yes, but it's not as straightforward as you might think. The principles of quantum mechanics can be extended to macroscopic objects, but the effects are much harder to observe.
Can you give an example?
Well, let's take superposition as an example. In the quantum world, particles can exist in multiple states at once. This is also true for macroscopic objects, but the difference is that the different states become so complex that it's impossible to observe them all at once.
That sounds like a problem. How can we use quantum mechanics to study macroscopic objects if we can't even observe their different states?
One approach is to use what's called a quantum macroscopic superposition. This involves creating a system where a macroscopic object is in a superposition of two or more different states, but the states are chosen in such a way that they interfere with each other and can be observed. This approach has been used to observe quantum behavior in objects as large as small diamonds.
I see. But what about the uncertainty principle? Does that still apply at the macroscopic level?
Yes, it does. In fact, the uncertainty principle becomes even more important at the macroscopic level because the objects are so much larger. This means that the uncertainties in position and momentum become much greater, making it even harder to observe the quantum behavior.
I can see why studying quantum mechanics at the macroscopic level is so challenging. But it's fascinating to think about what we might learn if we can overcome these challenges.
Yes, I think so too. The potential applications for quantum mechanics at the macroscopic level are still largely unknown, but I think it's an exciting area of research.
Tesla, have you heard about Bose-Einstein condensates?
Yes, I have, but I'm not quite familiar with it. Can you enlighten me on that, Einstein?
Sure, Tesla. Bose-Einstein condensates are a state of matter that occurs when a group of bosons, which are particles with integer spins, are cooled to a very low temperature and their quantum properties become apparent.
I see. What kind of quantum properties are you referring to, Einstein?
Well, for example, when bosons are cooled to such low temperatures, they start to behave like a single entity and occupy the same quantum state. This is known as the Bose-Einstein condensate.
Interesting. What are the practical applications of Bose-Einstein condensates?
Bose-Einstein condensates have a wide range of applications, such as in quantum information processing, quantum simulation, and precision measurements. They also provide insight into fundamental physics, such as the study of superfluidity and superconductivity.
That sounds fascinating, Einstein. How are Bose-Einstein condensates created and studied?
Bose-Einstein condensates are created by using lasers to cool and trap a cloud of bosonic atoms. The cloud is then further cooled to a temperature just above absolute zero, where the bosonic atoms occupy the same quantum state. Their behavior can be studied using various techniques such as absorption imaging and time-of-flight measurements.
Thank you for the explanation, Einstein. It seems like there is much to explore in the world of quantum mechanics, especially when it comes to collective quantum behavior.
Indeed, Tesla. The study of quantum mechanics has opened up a whole new world of possibilities and has deepened our understanding of the nature of reality. Now let's move on to the topic of quantum gravity. Quantum mechanics and general relativity are the two pillars of modern physics, but they don't fit together seamlessly.
Yes, that's because general relativity is based on the concept of gravity being a curvature of space-time, while quantum mechanics deals with the behavior of particles on a very small scale.
Exactly. In order to unify these two theories, we need to develop a theory of quantum gravity. However, this is still a major challenge for physicists.
Why is it so difficult?
Well, one reason is that we don't have a clear experimental observation of quantum gravity yet. Also, the math involved in combining general relativity and quantum mechanics is incredibly complex.
But what are some of the proposed ideas for a theory of quantum gravity?
One of the most promising ideas is string theory, which proposes that the fundamental building blocks of the universe are one-dimensional objects called strings.
And how does string theory account for gravity?
In string theory, the graviton, which is the theoretical particle that carries the force of gravity, is also a string. So, in a way, gravity is just another aspect of the behavior of strings.
I see. But is there any experimental evidence for string theory?
Not yet, but the theory is still being developed and refined. Another theory that's gaining some traction is loop quantum gravity, which proposes that space is made up of tiny loops.
And how does loop quantum gravity account for gravity?
In loop quantum gravity, gravity is a result of the interactions between these tiny loops. It's a bit harder to explain than string theory, but it's also a very promising approach.
Fascinating. It seems like we still have a lot to learn about the universe.
Indeed, the more we learn, the more we realize how much we still don't know. But that's the beauty of science, isn't it? Loop quantum gravity is a promising approach to unify quantum mechanics and general relativity. It is based on the idea that space-time is made up of discrete, indivisible units.
Yes, loop quantum gravity assumes that space is not continuous but is composed of tiny, interconnected loops. The theory proposes that the smallest possible length of space is about 10 circumflex 35 meters, known as the Planck length.
That's correct. In loop quantum gravity, the curvature of space-time is quantized, meaning that it can only take on discrete values. This is in contrast to general relativity, where space-time is smooth and continuous.
Another interesting feature of loop quantum gravity is that it predicts the existence of a fundamental particle called a graviton, which is responsible for the force of gravity.
Yes, that's right. Unlike general relativity, which treats gravity as a curvature of space-time, loop quantum gravity treats gravity as a force mediated by particles. This is similar to how the electromagnetic force is mediated by photons.
Loop quantum gravity also suggests that space and time are not separate entities but are intimately connected, forming a four-dimensional fabric known as space-time.
Absolutely. In loop quantum gravity, the fabric of space-time is made up of tiny loops, each of which interacts with its neighbors to form the continuous fabric of space-time that we observe macroscopically.
It's fascinating to think that the universe could be made up of discrete, indivisible units of space and time, and that our smooth and continuous experience of space-time is just an illusion.
Indeed, loop quantum gravity is still an area of active research, and there is much we still don't know about how it can be reconciled with other areas of physics, such as quantum field theory. But it offers a tantalizing glimpse into the fundamental nature of the universe. Another fascinating aspect of modern theoretical physics is the pursuit of unifying all the forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. Have you heard of string theory, Tesla?
Yes, I have. It posits that everything in the universe is made up of tiny one-dimensional strings rather than point-like particles.
Exactly. String theory proposes that the fundamental particles of matter are not point-like particles, but rather tiny oscillating strings. These strings can vibrate in different patterns, and it is these vibrations that give rise to the different particles and forces we observe in nature.
That's fascinating, but how does string theory attempt to unify the forces of nature?
Well, In string theory, gravity is not a force that exists independently of the other forces, but rather is a result of the way the strings vibrate. This is very different from traditional theories of gravity, which treat it as a force that is separate from the other fundamental forces.
I see. And what about the other forces?
The other forces are unified in a similar way through the vibrations of the strings. In fact, string theory predicts the existence of particles known as gravitons, which are the force-carrying particles of gravity, just as photons are the force-carrying particles of electromagnetism.
And has string theory been experimentally confirmed?
Unfortunately, not yet. String theory remains a highly speculative theory, and there is currently no experimental evidence to support it. However, it remains an active area of research and is seen by many as a promising avenue for unifying the forces of nature. So, Tesla, we know that black holes are objects with such strong gravitational pull that not even light can escape. But what does quantum mechanics have to do with them?
Ah, yes, black holes and quantum mechanics are intertwined in many ways. One of the most fascinating connections is the so-called black hole information paradox.
Information paradox? What is that?
Well, according to classical physics, if we throw an object into a black hole, it's lost forever. But in quantum mechanics, information is never really lost. Instead, it's always conserved.
That's true, but what does it have to do with black holes?
In the 1970s, Stephen Hawking showed that black holes actually emit radiation, now known as Hawking radiation. This radiation carries away energy and information from the black hole.
Interesting, but if information is conserved, doesn't that mean it violates the laws of physics for a black hole to emit radiation and lose information?
Exactly, that's the paradox. Some physicists believe that the information isn't lost, but is instead encoded in the radiation emitted by the black hole.
That's a fascinating idea, but is there any experimental evidence for it?
Not yet, but it's an active area of research. Some believe that the holographic principle, which states that all the information contained in a region of space can be described by a boundary surface around that region, may be relevant.
I see. It seems that black holes continue to reveal more and more mysteries even to this day. Let's talk about quantum cosmology. How does quantum mechanics relate to the origin of the universe?
Well, in classical cosmology, we use general relativity to describe the behavior of the universe on a large scale. But when we look at the very beginning of the universe, we need to take into account the effects of quantum mechanics.
Yes, I remember reading about this. It's called the quantum origin of the universe, right?
Exactly. The idea is that the universe began as a quantum system, which evolved over time to the classical system we observe today. But to fully understand this process, we need a theory of quantum cosmology.
And what would this theory entail?
One idea is that the universe can be described as a wave function, just like particles in quantum mechanics. We could then use the Schrödinger equation to describe the evolution of the wave function over time.
I see. And what implications would this have for the origin of the universe?
Well, one of the most interesting implications is that the universe may have arisen from a quantum fluctuation. According to this theory, the universe started as a tiny quantum fluctuation, which then expanded to become the universe we know today.
That's quite fascinating. It would mean that the universe has a quantum origin, just like particles and fields.
Exactly. And it would also mean that the universe has a fundamental randomness to it, just like quantum mechanics predicts.
But what about the deterministic laws of classical physics? Wouldn't this contradict them?
Not necessarily. It's possible that classical laws emerge from quantum mechanics on a larger scale. In fact, some theories suggest that quantum mechanics is the fundamental theory of nature and that classical physics is just an approximation of it.
I see your point. It's definitely a fascinating area of research, and one that could potentially unify quantum mechanics and general relativity.
Yes, it's an exciting time for physics. We still have much to learn, but I think we're on the right track. Einstein, I have been reading about the connection between quantum mechanics and consciousness. What do you think about it?
It is an interesting topic, Tesla. The idea that consciousness plays a role in the behavior of quantum particles has been debated for years. However, I personally don't believe that consciousness can directly affect the behavior of particles.
But what about the observer effect? Doesn't it suggest that the act of observation influences the outcome of a measurement?
Yes, the observer effect is a well-known phenomenon in quantum mechanics, but it doesn't necessarily imply that consciousness is involved. It can be simply explained as the interaction between the measured system and the measuring apparatus.
I see your point. But there are some physicists who believe that consciousness plays a more fundamental role in the universe. They suggest that consciousness and matter are interconnected in a way that we don't yet understand.
That's an interesting hypothesis, Tesla, but it lacks empirical evidence. I think we should stick to what we can observe and measure. There is still much we don't know about the universe and quantum mechanics, but we need to approach it with scientific rigor and skepticism.
I agree with you, Einstein. As scientists, we need to keep an open mind and continue to explore the mysteries of the universe. Who knows what we might discover in the future?
It's interesting to consider how quantum mechanics challenges our traditional understanding of reality. The idea that particles can exist in multiple states and that our observation of them affects their behavior is truly mind-bending.
Yes, it seems to suggest that reality is not as objective as we once thought. Rather, it is intimately connected with our perception and observation of it.
And yet, there are still some who cling to the idea of an objective reality separate from our observation of it.
Perhaps they simply haven't yet grasped the full implications of quantum mechanics. But it seems to me that the idea of an objective reality is fundamentally flawed. Reality is inherently subjective, and our understanding of it is always shaped by our own experiences and perspectives.
That's an interesting perspective. But what about the laws of physics? Are they not objective and universal, regardless of our observation of them?
Of course, the laws of physics are universal, but our interpretation and understanding of them are still influenced by our subjective experiences and perspectives.
I see your point. It's important to remember that our understanding of reality is always evolving, and quantum mechanics has forced us to rethink some of our most basic assumptions.
Yes, and I think that's a good thing. It's important to always question our assumptions and be open to new ideas, especially in fields as complex and mysterious as quantum mechanics.
Agreed. The study of quantum mechanics has taught us that reality is much stranger and more mysterious than we could have ever imagined. But it's also given us a glimpse into the true nature of the universe, and that is truly awe-inspiring.
Well, it has been an enlightening conversation, Einstein. Thank you for sharing your knowledge and thoughts on quantum mechanics with me.
Likewise, Tesla. It's been a pleasure discussing these ideas with you. Quantum mechanics has brought about a lot of new concepts and opened up new possibilities for understanding the universe.
Yes, indeed. It's fascinating to think that particles can exist in multiple states at once and the role of measurement in affecting particle behavior.
And let's not forget the wave-particle duality of light and matter and the intriguing concept of entanglement.
Quantum mechanics has also led to the development of technologies like quantum computing and cryptography, which have the potential to revolutionize fields such as information technology and medicine.
And while there are still many unanswered questions and debates around the interpretation of quantum mechanics, it has brought about a new perspective on the nature of reality.
It's always exciting to learn about new theories and ideas, and I look forward to seeing what discoveries will come next.
Agreed, Tesla. Well, it's time for me to get back to my research. Until next time.
Farewell, Einstein. Keep up the great work.